Hello everyone, welcome back to ACER Explained. I'm going through section 3 of the ACER Practice Question booklet, and in this video I'm going through Unit 12. So Unit 12 consists of questions 29 to 33. As always, I'll be identifying prerequisite knowledge that you might need, reasoning skills, as well as some of the bootcamp resources that you can use as well. So Unit 12 has given us a table of reduction potentials, as well as what it means. So we have positive reduction potential means that the system is more easily reduced than hydrogen, and a negative reduction potential means that the system is less easily reduced than hydrogen. And if we have any two redox reactions that are combining, then the more positive reduction potential, whichever half reaction has the more positive reduction potential, that's the one that will end up being reduced. The other one will end up being oxidized. So we have the question of what would happen if you add Br2 to a solution of Cl and I. So looking at the reduction potential table, we have 1.07 for Br2. Then we have 1.36 for chloride. Then we have 0.54 for iodine. And so when you add this to a solution of these ions, this is going to be the one that is reduced because you're starting off with this, right? You're starting off with the left-hand side of the equation. So you have Br becomes the ions. These already start in their ion form, and so they go kind of backwards in their half reaction and they get oxidized. But we have to pick one. So we know that Br2 is going to be reduced, so we can eliminate option C. And then we have the other two options here. Now, this is more positive than this one here, but it's less positive than this one here. So because this is more positive than the iodine, it means that Br2 will be reduced and act as the oxidizing agent and result in iodine being oxidized. The chloride reduction potential is greater than that of bromine, and so nothing's going to happen to chloride. So the answer is B. So with this one, there's no real previous knowledge that's required. Redox reactions can be helpful to know about so that you're familiar with this concept, but essentially we use the process of elimination as well as extracting the relevant information in order to answer the question. So then the bootcamp resources that would be helpful for this are the reasoning skills course as well as the bridging course on cells and redox reactions. Question 30 is quite similar. It's basically asking what would happen or which of the following, so looking at these three, would allow hydrogen ions to be reduced to hydrogen gas. And so we know from the reduction table that the reduction potential of this is 0. Then we just have to look at these three options. So we have positive 0.54 here. Then we have positive 0.34 here, and we have negative 0.76. And we know that, so we want this to be a reduction reaction, and we know that the reaction, the half reaction that is more positive is going to be reduced, and the one that is less positive is going to be oxidized instead. And so we need an oxidizing half reaction in order for this to be reduced. Because you need to have electrons being transferred. So we can't have two reductions happening at the same time. We need to have an oxidation happening so that a reduction can happen. And the oxidation would have to be more negative than 0. We only have one option here. And so the answer is C. So with this one, there's no real previous knowledge that's required. Redox reactions can be helpful to know about so that you're familiar with this concept, but essentially we use the process of elimination as well as extracting the relevant information in order to answer the question. So then the bootcamp resources that would be helpful for this are the reasoning skills course as well as the bridging course on cells and redox reactions. Questions 31 and 31 to 33 have an additional table that they've given us of reduction potentials. And these are for some organic molecules. And the question itself, so question 31, is asking us for the strongest reducing agent. So we're going to go through one by one and look at their place in the table. So with option A, this molecule shows up in the fourth row of the table and it's being reduced. And the reduction potential is negative 0.20. Okay. This here, option B, shows up in the third row and it's a product of a reduction reaction, which means that this itself is going to be oxidized. Okay. And the reduction potential for this reaction as a whole is negative 0.19. Okay. Then we have option C, which shows up in row 2 of our table. And this is also a product of a reduction reaction, so it's going to be oxidized if it's left alone. Or if it's present in that reaction, it's going to be oxidized and go in the opposite direction. And the reduction potential for this reaction is positive 0.03. And then finally, we have option D. And option D shows up in the fourth row of our table, and it's the product of a reduction reaction. So again, it's going to be oxidized. And the reduction potential here is negative 0.20 as well here. Okay, so the question is asking for the strongest reducing agent, right? So a reducing agent is an agent that is oxidized because you need to have an oxidation to lead to a reduction. So this is a reduction reaction, so we can eliminate this. We need to look for molecules that are going to be oxidized. Then we have the rule that we read earlier, which was that the most positive reduction potential, the more likely that it's going to be reduced. That reaction, that half reaction is going to be a reduction reaction rather than an oxidization reaction. So we're looking for the least positive here if we want to look for the best oxidizing agent, right? Sorry, reducing agent. So we want it to be oxidized more. So the least positive one here is the negative 0.20. And so this is our correct answer. So this is the least likely to be reduced, the most likely to be oxidized. Therefore, it's our strongest reducing agent. So with this one, there's no real previous knowledge that's required. Redox reactions can be helpful to know about so that you're familiar with this concept, but essentially we use the process of elimination as well as extracting the relevant information in order to answer the question. So then the bootcamp resources that would be helpful for this are the reasoning skills course as well as the bridging course on cells and redox reactions. So for question 32, we're given two equations here. We're given this equation, and then we're given this reaction equation. And the question is asking us to find KEQ for this particular reaction. It also tells us that N is the number of electrons that are transferred. So the way that I figure out the electrons is, first of all, I'm going to start off by looking at what's different on the left side versus the right side. So we have this molecule here that changes to this molecule, and you have two hydrogens that are being transferred onto this oxygen. Okay, so you have this hydrogen here, and this becomes one. So that's two hydrogens. Okay, and that means that with this hydrogen transfer, because this is two protons essentially, in order to balance this out, you have two electrons that are being transferred. I don't really, for this equation or for this question, need to look at exactly what's being reduced versus oxidized, etc. Right now, I'm only caring about the electrons, and for the sake of speed, I would look at 2 hydrogens and think 2 electrons and move on, okay? So then I would fill in the gaps. So we're already given this value here. So we're given 1.02 is equal to 0.06 over n, and log 10, we need to find out what KEQ is. All right, so I'm going to start off by putting in 2 here for our n. So we know that this is 0.03. And then I'm going to divide it on both sides. So I would do 1.02 divided by 0.03, and then I've divided this side by 0.032, so I can cancel that out and go log 10 KEQ. So just cleared up the board here. What I would do now is solve for this, and I don't like decimals, so I would multiply both the top and the bottom by 100 to get 102 over 3, and then I can do kind of my long division for this. So I would do this probably in my head, but just to show you the working out, I would put 9 here and then 1, and then bring that down, and that's 4. So then I have 34 is equal to log base 10 multiplied by KEQ. Then I would have to take the inverse log of both sides in order to get KEQ. And because it's log 10, I know that taking the inverse will just get me to this, 10 to the power of 34 is equal to, and then if I inverse log this, then it would be KEQ. So the way that you can double check this is by going log 10 of 10 to the power of 34 is equal to what? It's equal to 34. Okay, and so there you go. And then obviously, if you take the log of this side, you're just going to get log 10 KEQ, which is the same thing as you have here. So that means KEQ is 10 to the power of 34. And so the answer is D. Again, this one didn't require too much previous knowledge. However, with the number of electrons being transferred, it would be helpful if you've done this before so that you can quickly figure out how many electrons are being transferred without kind of having to do all of the in-between steps and figure that out that way. And you also needed to know a little bit about your basic logarithms. Logarithms come up a lot in the GAMSAT, so I would definitely recommend getting familiar with those. And you can find those in our math bridging courses. But other than that, we have our reasoning skills course, our cells and redox reaction bridging course, as well as our moles and calculations bridging courses, which are relevant to this question. So question 33 gives us some additional information as well. We're given these molecules here and their reduction potentials, but we don't know whether it's negative or positive. It's only a magnitude, okay? And we're given some information as well. So we're given the information that when this half cell, so the MM2 half cell, is attached to a standard hydrogen electrode, then the electrons will flow away from this towards this, okay? And so if we remember, the hydrogen reduction potential is 0 volts. And so we just need to figure out whether this 0.26 is negative or positive. For this, it's easier to figure out oil rig. So we have oxidation is loss. So this is something that is quite handy from your redox chemistry. And then reduction is gain of electrons. Okay, so because the electrons are flowing away, this is getting oxidized. Okay, so they're losing electrons, so it's being oxidized. Now, the hydrogen electrode is gaining these electrons, so this means that it's being reduced. Okay, so it's being reduced. And as we know from earlier, we know that the half reaction that gets reduced is going to have the more positive reduction the reduction potential. Okay, so the more positive reduction potential, it's going to get reduced, which means that this must be less than 0. So it must be more negative than 0, which means that it can only be this option here. So it's going to be negative, not positive. Okay, because if it was positive, then it would be more positive than the hydrogen electrode, and it would get reduced instead of the hydrogen electrode being reduced. And then we have another kind of scenario that they've given us where we have electrons flowing from this cell away from it towards the N half cell. Okay, so we have negative 0.26 volts. We have 0.34, not sure if it's negative or positive volts, but we know that this side is getting reduced and this side is getting oxidized. And the side that is getting reduced must be more positive than the side that's getting oxidized, right? And so if this was a negative sign here, then it would be less positive than the M half cell. But we know that it's getting reduced, and so it has to be more positive, and so we can say that this one has a positive sign. So just clearing the board again, now we have our reduction potential values, and the question is asking us what would be the cell potential of a cell with these two half cells combined. So for that, we have our equation that we've used before. And we have, okay, and so what you would do there is just find the difference. So we have 0.34 minus negative 0.26. And so this is if you're using the reduction potential, it remains a minus. If you yourself flip the sign because you know that the reduction potential should be flipped for oxidation, then you can add them, if that makes sense. Or you can just subtract them like this. Okay, but let's go with the subtracting. So we have 0.34 plus 0.26, and the answer there is A. Awesome. And for this question, it really would help if you have some knowledge of that oil rig, so the redox reactions, but you are given that information in the stimulus, so you still can figure it out. And you just had to extract the relevant information to answer the question. And so that involved, knowing what to do with those sentences that kind of described the different half cells. Being able to kind of draw that out is helpful. And then obviously just doing your basic calculations. So as always, we have the reasoning skills course, but then also the cells and redox reaction, as I've been mentioning throughout this video, and the moles and calculations. Those could be really helpful for this one. So that's the end of Unit 12. Please like, share, and subscribe for more GAMSAT help, and give us some feedback because that's always very useful. And we have our Instagram there at ThankFlipGamSat, as well as our podcast, ThankFlipGamSat, Nurses Doing GAMSAT. And I'll see you in the next one.